So far, we have been focusing on what it will mean for us to talk about algorithm complexity. And we have settled on the intuitive idea that we are going to look at the way the time it takes to run an algorithm changes when the data size becomes bigger. Usually this time will grow, but it can grow, as we have seen, in different ways. We spent some time looking at an algorithm that grew in what we called a linear way. It was a list traversal algorithm, and it needed the same time to process each of the elements in one list, so it grew in a linear way when the size of that list, of that data, grew. That is going to be what we call our first complexity class. What is a complexity class? Well, basically it's just a group where we put together all of the algorithms that grow in the same way when their data size grows. All the algorithms that do that loosely follow a line when the data size grows, are going to be called linear complexity algorithms. And we are going to note them with a big O and an N. The big O just means we are speaking about complexity in one very particular way, and you can go and follow the references in the notebooks to see the very precise definition of what that means mathematically, but today I'm just going to stay with the intuition. Okay, and all of those algorithms that follow a line when their data size grows, we're going to call them linear type algorithms, linear class complexity algorithms. One important thing to say here is that we are going to be speaking about worst case complexity. Okay, what does that mean? So far, we didn't have any problems because my algorithm always behaved in the same way. I had to traverse all the algorithms in my list once and only once. But what happens if my algorithm has alternatives and behaves in different ways depending on my data? For example, what happens if I have a search algorithm? I'm searching for an element, let's say 55, in a list. Well, what happens is that sometimes I finish here, I traverse all of these algorithms and end up here because I find 55, and if I was looking for 5, I would end up here, so I would only have to look at one element, and if I was looking for an element that is not there, for example, let's say 27, then I would have to traverse all the all the elements and finish because I had not found the element I was looking for. How should I talk about the computation time of this algorithm? Should I say that sometimes it's 1, sometimes it's more, and sometimes it's the full length of the list? Well, that would be confusing, and although there are different ways to solve this, we are going to go with the following one. We are always going to speak about worst case complexity. So in this case, we are going to say that this algorithm is linear because in the worst case, I'm going to have to look at all the elements in the list, and I'm going to take exactly the same time that I was taking before. Okay? So we are going to be using worst case complexity. Okay? And we have seen linear complexity already. But that's not the only class that we are going to see in this session. We are going to see one more before we finish, and in the following sessions we are going to see many more when we study different types of algorithms, and mostly we will do that by using the problem of sorting a list of integers. Okay, but as I was saying, let's see another complexity class. What would happen if I wanted to access one element in a list? As you know, if I know the position in the list, I can access that element directly. I don't have to traverse anything. I don't have to look for anything. I just go there. I tell Python, I want the, in this case, 7th element in my list, and it goes directly there. Okay. if I look for the second element, it takes exactly the same time. The 11th element, yes, the same time always. I'm going to say that accessing one element in a list is constant. Okay, what happens if my list is longer, if I have more elements in the list? Exactly the same. I can access any position in the same time. Python only has to go and look at the proper memory. It doesn't have to traverse anything. It just goes there. Okay. Consequently, this algorithm behaves differently when the size of data grows. Okay, there are our well-beloved spikes, but they are very, very small. And what happens when I access a list of length that grows is basically that it always takes the same time, regardless of the size of data. Okay, so this second class of algorithms don't grow their time when the data size grows. Okay, we saw before algorithms that have a linear behavior when the data size grows, and it doesn't matter if the line is slope 1 or half or 2. All of those are going to be grouped into this O of n class. And now we have seen another. All the algorithms whose time does not grow when n grows, when the size of data grows, are going to be called constant class algorithms, constant complexity algorithms. And I'm going to write that with big O of 1. We are going to be seeing many, many more complexity classes, and I have plotted some of them here. Sometimes this mathematical notation that we can understand that these functions show a behavior. Okay, this here we have the line that more or less we had seen before. Here we have drawn it nicely. Okay, these functions that describe the behavior can sometimes obscure what it means in terms of the difference between the time it takes to run one algorithm and the time it takes to run another. And to illustrate this a little bit, I have drawn the functions that represent some of the classes that we are going to see in this class, in this course, and I have drawn them together to illustrate a little bit the differences. For example, we have seen linear complexity, and we will see something called logarithmic complexity, which, as you can see here, is much faster, grows the time in logarithmic complexity, although here it's not easy to see, grows, but it does so much more slower than linear complexity. And if we go to something else called n log n complexity, this function that grows faster. And then if we go to the next complexity class that we will see, n squared, and we compare it to these two, we can see that that's much, much slower than the previous two. Okay, here the n1 is here. Okay, so this difference here gets converted into this small difference here if I compare everything to n squared, which is much, much slower, as we will see with the bubble sort and insertion sort algorithms. Okay, and what happens if I had not a linear and not a square, not a quadratic, but a cubic time algorithm? Well, it would be much, much slower. This huge difference here gets transformed into this very tiny difference there if we compare it to the n to the cube. So the behavior that algorithms have when the data size grows has a real effect on the computation time, and we are going to be seeing this. Very particularly, we are going to try to design algorithms that are as fast as possible, because otherwise you can end up with things like complexity class e to the n, which is this, and leaves poor old n squared and n3 here looking flat because e to the n is so big. We are going to see some algorithms there. We are even going to see some algorithms that are both e to the n and that are optimal for their problem. Okay. So we have given the intuition behind the idea of algorithm complexity that we are going to use. We are going to write it down with big O of n, and we are going to group the algorithms according to that idea, how their computation time changes when the size of data grows. We have seen in this unit that traversing a list to compute, for example, the average has linear time complexity, which is the complexity that happens when the computation time of the algorithm grows following a line. And we have also seen that accessing a list is constant time complexity. The computation time for that doesn't change if the list is longer.